Hey everyone, welcome back. In this video, we are going to walk you through Trossen ARM software update 1.8. And there's a lot to cover. Let's start with the new effort mode. But how exactly is it different from the external effort mode? While the external effort mode includes built-in compensation for things like gravity and friction, in the effort mode you can send raw effort commands directly to the motors without any compensation. This gives you full control over torque, which means it's perfect for designing custom controllers, test rigs, and setups where you don't want the system interfering with your logic. Next, we have completely reorganized how the robot outputs are handled. All the robot outputs are a part of a single class called Trossen ARM robot output. You now get access to much more detailed information like joint level compensation efforts, rotor temperatures, driver temperatures, Cartesian position, velocity, and external efforts. This makes the data access much more clean, structured, and scalable. Now let's talk about how you can access all the new robot state outputs, and it's really well organized. You can retrieve things like position, velocity, external efforts, compensation efforts, rotor temperatures, and driver temperatures, all using a consistent naming pattern. Here's how it works. If you want data for all your joints, including the arm and the gripper, just use get all prefix. So for example, get all position, get all velocities, or get all efforts, and so on. If you want data for just the arm, excluding the gripper, use the get arm prefix. Get arm position or get arm driver temperature. To access values for just the gripper, use the get gripper prefix. For example, get gripper effort or get gripper rotor temperatures. If you need to fetch values for a specific joint index, then use get joint methods like get joint position, get joint efforts, get joint compensation efforts, where you pass the index as the argument. In addition to joint space values, we also have Cartesian outputs. So if you are working in a tool space like controlling the end effector or monitoring its movement, you can use the get Cartesian methods. For example, get Cartesian position, velocities, or external efforts. All of these follow the same naming structure, so once you get used to one, the rest of them are easy to pick up. This really simplifies the logging, diagnostics, and control logic of your code, and makes the API really intuitive to work with. Next up, let's talk about the Cartesian-based control. This update introduces a set of really cool features that allow you to control the robot directly in the tool space relative to the end effector's frame. Now, why is this important? Most of the high-level tasks, like reaching a point in space or applying force on a surface, are best expressed in Cartesian coordinate systems. Instead of controlling each joint individually, you can command the position, velocity, or effort of the end effector tool and let the system take care of the inverse kinematic. There are 3 modes supported in this update. The Cartesian position. This lets you specify a target position and orientation for the tool frame, and the arm will move there using the internal planning. This is great for precise object placements, point-to-point movements in the task space, and teaching motions intuitively. Here's an example of Cartesian position control in action. We send a pose command and end effector moves smoothly to that position. You can find this demo in the script named cartesianposition.py inside the demos folder of the Trossen ARM repository. The Cartesian velocity. This mode allows you to glide the end effector in a direction with a specified velocity vector. This is perfect for continuous motion, interactive or joystick control, and dynamic adjustments during runtime. In this demo, we use the Cartesian velocity control to simulate a spring mass damper system, also known as admittance control. The arm reacts to external forces by updating the velocity in real time, making it behave like it's attached to a virtual spring. Just a quick note, this is a toy example. The gains used here are for demonstration only. Poorly tuned stiffness or damping values can lead to unstable or unexpected arm behavior, so adjust with caution. And finally, we have the Cartesian external effort mode. This is used to apply desired force or torque at the tool frame, often used for force control tasks. This is useful for contact-sensitive tasks like wiping, pushing, or interacting with uncertain surfaces. Also used in compliant control, shared autonomy, or haptic application. This demo shows how to use Cartesian external effort control to simulate a virtual spring commonly referred to as impedance control. This script sets up a simple second-order system using stiffness and damping value and commands external forces based on the differences between the current and the target force. You'll find this in the Cartesian external effort.py script. Again, a quick reminder, these gains are for demonstration purpose only. Improper tuning can lead to unstable arm behavior, so always test carefully. All these scripts like Cartesian position, Cartesian velocity, Cartesian external efforts are available out of the box for you. You can find them in the official Trossen ARM repository, and they are well documented so that you can change them according to your use case. This new Cartesian control support makes high-level behavior much easier to implement, especially in learning-based or reactive control scenarios. Now let's move on to the next feature. Sometimes during the development or flashing the firmware, you might need to reset your control box. With this update, you can now trigger a software reboot without physically needing to power cycle your control box. It's a simple and reliable way to bring back your system to a clean state when needed. Here's how it works. To perform the software reboot, all you need to do is to set the reboot controller flag to true in the cleanup method. This will automatically trigger a soft reset of your control box. No need to unplug or manually power cycle anything. We have also added and revised a number of configuration parameters. You now have more control over joint limits, motor parameters, algorithm level settings, end effector properties like pitch circle radius and tool flange transforms. A few outdated ones like continuity factor and Tmax factor have been removed for clarity. These changes give you fine-grained control over how the ARM behaves in different operating conditions. For C++ users, we have changed all the numerical data types to double precision from float. This small change makes a big difference, especially when you're working with libraries that expect double by default, like Eigen, MoveIt, and many other optimization libraries. It also improves the numerical stability for high-precision tasks. No change needed for Python users, but for C++ users, make sure your data types align with the ones in the API drivers. Also, just a quick note, if you are using the older getter methods like getPosition, getVelocity, getExternalEfforts, getEfforts, or getCompensationEfforts, these are now deprecated and will be removed in the next major update. So now is a good time to switch to the new structured and cleaner getter methods that we just discussed. To wrap things up, this update brings you several important things on both the controller and the driver side. Support for the new effort mode is fully integrated. You also get the rotor temperatures and the driver temperatures directly in the output. Soft reboot is now supported through a simple configuration file. New configuration interfaces are exposed, giving you more control over the joint limits and the motor parameters. We have also added input and output checks that allow you to catch things like infinite values or joint limits violations. The older continuity check has been removed. Communication has been made simple and robust. UDP is strictly used for real-time control and TCP is used for handling the data exchange. If the connection drops, the controller safely returns to idle mode. Lastly, default configurations have been revised to use more practical values, especially for the joint and the motor limits. That's everything for this update. Thanks for watching, and as always, feel free to check out the demos, dig into the documentation, and see you in the next one.
Trossen Robotics, helping innovators innovate.